In lecture 14, we look at methods of numerical integration, and this allows us to approximate integrals of the form the integral from a to b, definite integrals, f of x dx, especially in cases where we can't find an antiderivative to this function f of x in order to evaluate the integral. And we already have some methods. From Calculus 1, we've already looked at some methods of making a numerical approximation to the definite integral. In particular, we used Riemann sums, and we looked at left endpoint approximations, right endpoint approximations, and midpoint approximations. And in this class, we're going to review the midpoint rule. And the formula is shown here. If I want to get what I call the midpoint approximation to this definite integral from a to b of f of x dx with n approximating rectangles, the formula for that is the sum from 1 to n of f evaluated at the midpoint times delta x. And delta x will be the length of the base of the approximating rectangle, and it will be the length of the interval b minus a over the number of approximating rectangles. And so the formula expands to delta x times f evaluated at the midpoint of the first approximating rectangle plus f evaluated at the midpoint of the second, etc., plus f evaluated at the midpoint of the nth approximating rectangle. Geometrically, this is what's going on. If I want the midpoint approximation to the integral from 0 to 2 of 5 times the cube root of x dx with 4 approximating rectangles, what I do is I carve this interval from 0 to 2 into 4 equal parts, and each of those subintervals has length delta x, which is 2 minus 0 over 4, where 4 is the number of approximating rectangles. So each one has length 1/2, and then I construct a rectangle above this subinterval, above each subinterval, and the height of that rectangle is the value of the function at the midpoint of the subinterval. And the midpoint is the sum of the two endpoints of the subinterval over 2, and then to get the height of this rectangle, I evaluate f at that point. And then my approximation is to sum the areas of these 4 rectangles. And you can see that in some places they overshoot the curve and in some places they undershoot. And one would expect that we would get a pretty close approximation to the area under the curve here. And here the computer has calculated the exact area because it can compute the limit as n tends to infinity of this process, where n is the number of approximating rectangles, and we know from Calculus 1 that that limit is the actual value of this definite integral. So we know the exact area is 9.44941, and the sum of the area of these 4 rectangles is pretty close. It's 9.55202. So it's over a little bit, and the actual value of that error is 0.103. If I were to take a larger number of rectangles, then I should get closer to the actual value of the area, and then as the number of rectangles tends to infinity, then the sum of the areas of these rectangles tend towards the actual value of this definite integral. In fact, we can use that as a definition of the definite integral. And again, as the number of approximating rectangles gets larger, the error in our approximation gets smaller. we'll introduce two other methods of approximation, numerical approximation. The first one is the trapezoidal rule. And so here, instead of approximating with n rectangles, we approximate with n trapezoids. And so we construct a trapezoid above each subinterval. The height of this trapezoid above the left endpoint is f evaluated at the left endpoint, and the height above the right endpoint is the value of f at the right endpoint. And you can see the top of this trapezoid joins these two endpoints with a line, with a straight line, and this sort of follows the curve, but obviously leaves a little error here in the area, since the curve here is not linear. So the idea is that the sum of the areas of these trapezoids should be close to the integral from a to b of this particular function f of x. Now the algebraic formula for this rule is we have the integral from a to b of f of x dx is approximated by the trapezoidal rule applied with n approximating trapezoids, and then that is equal to the approximation is given by the sum of the areas of these trapezoids. And the area of the trapezoid between x0 and x1 is delta x, which is, as before, the length of the base of the trapezoid. It's b minus a over n times f of x0 plus f of x1 over 2. And if you think hard about it, it's not too difficult to figure out that this is the area. In fact, it's the average of the areas of the two rectangles, the left endpoint rectangle and the right endpoint rectangle here. So I'll leave it to you to figure out why this is the area of the trapezoid. And you see, for each of these trapezoids, if you add their areas, you get, the first one gives you f of x0 plus f of x1 over 2 times delta x, and the second one gives you f of x1 plus f of x2 over 2 times delta x. So you see, when you add, f of x1 appears twice in the formula. Also f of x2 appears twice, right down as far as the second last marker here, f of xn minus 1, and then f of x1 appears only once because the area of the last trapezoid occurs once, and the right endpoint just occurs once in the calculation. So we end up with this formula for the trapezoidal rule. To apply it, we first calculate delta x, the length of the interval over n. We calculate the xi's, which usually it's easier to calculate them geometrically. Just picture the interval and divide it into n equal parts. And x0 is the left endpoint, x1, x2 down as far as xn. And then we evaluate f at each of these endpoints of the subinterval. And our trapezoidal rule says that the trapezoidal approximation to the definite integral is delta x over 2 f of x0 plus 2 times f of x1 plus 2 times f of x2, etc., plus 2 times f of xn minus 1 plus f of xn. So when applying this to say something like the integral from 1 to 4 of 1 over x dx with n equals 6, we first calculate the delta x, then we calculate the endpoints of the subintervals, and we calculate f at each of those endpoints, and then we apply our formula, T6, the approximation, the trapezoidal approximation to the integral from 1 to 4 of 1 over x dx, with 6 approximating trapezoids, is delta x over 2 times f of x0, which is 1, plus 2 times f of x1, which is 2 times 2 over 3, etc., etc. Fill in the details, and we find it's 1.405357143. Now there is of course an error in this approximation, as there is with all approximations. And here we see the trapezoidal approximation with, let's say, 8 approximating trapezoids to the integral from 0 to 2 of 5 times the cube root of x dx. And the exact area is 9.44941, and the approximate area using the trapezoidal rule T8 in this case is 9.23648. So we have an error of 2.13 times 10 to the minus 1. And we see here where the error is the greatest on the first trapezoid, because the curve is very different than a line here between 0 and 0.25. How does this compare to the midpoint approximation? Well, we see in fact that the error using the midpoint approximation here is 4.23 times 10 to the minus 2, and the error using the trapezoidal approximation is 2.13 times 10 to the minus 1. So the error with this trapezoidal approximation is actually greater than that with the midpoint approximation. And you'll find in general that the midpoint approximation is a very good approximation to use for these functions. We'll think about the error a little bit. Obviously, if we knew exactly what the error was, then approximating would be a little silly, because we would actually be able to find the actual value of the integral. And so we have two errors so far. We have an error associated with our midpoint approximation and an error associated with the trapezoidal approximation. And if you're working without your computer, how might you get some estimate of this error? And what we do have are some upper bounds for these errors. So if you calculate using either of these methods, we have some upper bounds if the function has a second derivative on the interval from A to B, and you have that an upper bound for the absolute value of the second derivative, let's call it k, so we know the absolute value of the second derivative is always less than or equal to k, then the errors for the trapezoidal and the midpoints approximation are bounded in this way. So we have the error for the trapezoidal approximation. Its absolute value is always less than or equal to k times the length of the interval cubed over 12n squared, and the absolute value of the error for the midpoint approximation for n approximating rectangles has to stay below k times the length of the interval cubed over 24 times n squared. And so this allows you to do two things. Number one, if you decide on the n and you approximate, then you have some information about the error. So you have an upper bound for the error, so you have some information about what kind of error you might be making. On the other hand, you might want to keep some limits on your error. So you might want to decide, well, I want an approximation which is accurate up to 6 decimal places. And this gives you a method of choosing n large enough so that the error can be less than or equal to 10 to the minus 6, or whatever you have in mind. So this is a tool you can use either to approximate or put some bounds or know something about the error after you've approximated, or else choose your n wisely so that you can keep your error within the bounds that you desire. We're also going to look at Simpsons Rule, and this is going a step further, and it uses the fact that given 3 points, there's a unique parabola passing through those 3 points. This is something you might have learned when you studied conics. It's true. Given any 3 points in the plane, there's a unique parabola which passes through those points. And so what we do is if I want to estimate the integral from a to b of f of x dx, and in this case f is positive, so it's just the area under the curve, I divide that interval up into an even number of parts. So here n is even, and for each 2 consecutive subintervals, I take the point on the curve above the left end point, above the right end point of the first subinterval, and then the right end point of the next subinterval, and I connect those 3 points with a parabola, and then I shade the region under that parabola. And then I take the area under that parabola as my approximation of the area under the curve on these 2 subintervals. And with the next 2 subintervals, I do exactly the same thing. I connect the 3 points on the curve directly above the endpoints of these 2 subintervals, and I connect those with a parabola, the unique parabola passing through those 2 points, and I shade the region under that parabola, calculate its area, and that is my approximation to the area under the curve above these 2 subintervals. So I do this for every pair of subintervals, and I find that the area of this parabola, stretching between xi minus 1 and xi plus 1, so it's got 3 of these endpoints encompassed, the area of that parabola is delta x over 3 times f evaluated at the left endpoint plus 4 times f evaluated at this middle point xi plus f of xi plus 1. And then I add the areas under these parabolas together, and that's Simpsons Rule. That's Simpsons' approximation to the integral from a to b, or the area under the curve between a and b here, of f of x dx. So in all, when I add these, Simpsons Rule, or Simpsons' approximation, is delta x over 3 times f of x naught plus 4 times f of x1 plus 2 times f of x2 plus 4 times f of x3 plus 2 times f of x4 plus 4 plus 2 plus 4 plus 2, and the second last one is 4 times f of xn minus 1 plus f of xn. So delta x is b minus a over n, and again xi is the endpoint of the subinterval a plus I times delta x. And we see here, if we apply Simpsons Rule to this, first thing is you need n to be even, so you need an even number of subintervals here, so we have 8, and so we put them together in pairs. Here we have the first 2, and we see the approximation is not as good as the others because these 3 endpoints, the curve between 0 and 0.5 here is not as close to a parabola as it is between 0.5 and 1 and so on. So we see the line of the parabola is here, and the area under that parabola is the purple area, and that's our approximation to the area under the curve between 0 and 0.5. Now for the other 3 parabolas, they run pretty close to the line of the curve, so they're a pretty good approximation to the actual area under the curve. So when I add the area of these four constructions with parabolic tops, I get that they add to 9.34166, and the actual area is 9.44941. And the error I'm making is 0.108, and let's compare that to the error I might make using the trapezoidal rule here. And you see the error with the trapezoidal rule is larger, it's 0.213, and the error with the midpoint rule is actually a little less here. It's 0.0423, and it's actually less than Simpsons rule. Let's try another function. Let's try sine of x and see how Simpsons rule works with n equals 8 approximating subintervals, and in this case you get 4 approximating constructions with parabolic tops, and we see that the exact area is about 1.416, and it's really well approximated by Simpsons rule. The error is 3.1 by 10 to the minus 5. Let's see how that compares to our midpoint rule. So in this case, Simpsons rule beats the midpoint rule. The error is actually larger with the midpoint rule, and we'll probably see that both of those beat the trapezoidal rule. So Simpsons rule in this case is more accurate than the midpoint rule, and of course as n tends to infinity it should get closer and closer to the actual value of the integral. Again, we have upper bounds on the error for Simpsons rule, so in class we'll apply it, apply the formula using a table, and we'll think about the error, and we also have an upper bound for the error. This time we know if the fourth derivative of the function has absolute value less than or equal to k on the interval, the error from the approximation we get using Simpsons rule with n approximating subintervals is less than or equal to k times the length of the interval to the power of 5 over 180 times n to the 4. So again, you can use that as a double-edged sword, either to consider how big the error might be after you've calculated Simpsons rule, or to think ahead a little bit and choose the n wisely so that you can keep your error under control.